Frank Sottile, Frank will talk about Galois groups in numerical geometry and the applications.
Okay, well, thank you very much for coming this morning. I want to thank you. I'm not in our school, of course. I want to say, however, is that I've been very deeply influenced by people who have come from that school or related to it, like Sottile and some of my collaborators. Also, growing up in the 1960s and 1970s, mostly 1970s, I could never imagine traveling. I don't come from a professional background. Traveling internationally or even meeting people from that time of the Soviet Union. And it's been a really remarkable thing for me as an adult that we can travel and interact fairly freely. I think that's really a good sign for the world. No matter what happens in any given year, it's still, I think overall, the arc has been very positive, at least in my lifetime. And I'm very pleased to be here talking to you. Let me get to some math. So, we all know that a Galois group is the symmetry group of a field extension. That's how we learned it. That's what they're defined to be. What's interesting is already in 1870, Jordan explained how he explained that the Galois groups. Oops, it's hard to spell when you're bored. Galois groups naturally arise in geometry, in enumerative geometry, which was an important subject at the time. So let me just explain by it with a classical example. So it's known that on a smooth cubic in three-dimensional projective space, so a cubic surface, there exists exactly 27 lines. That's the Cayley-Solomon theorem. We know the beautiful pictures and models of that. And these have maybe I should say remarkable, because in a remarkable configuration. I'm not going to detail, but some of the lines that some of them meet, some of them are disjoint. The numbers that meet, pairs of numbers and triples that meet or disjoint is quite special. It has a number of names, but because of this configuration, what Jordan realized. So let me explain. So my cubic is the zero set of a polynomial. This is my cubic. Where f is rational, I guess x naught, x3, so it's a rational polynomial of degree 3. And we know that the 27 lines are defined in some field extension.
Three-dimensional?
Yes, it's homogeneous cubic. So it defines a
dimension 3, right?
Yes. There are 4 variables for P3. So it's a cubic. It defines this cubic surface. Okay. If it's smooth, there are 27 lines, and they're defined in some extension K of Q. And so if I take the Galois closure. I don't know what the notation is. I don't really live in number theory. The Galois closure of K, then the Galois group of this Galois closure over Q, it acts on the lines. Okay, it's simply because it has to fix the rational cubic. Okay, and it permutes them, and this action cannot be the full symmetric group because it has to preserve this configuration. So it's preserving the configuration. So this is an example where the Galois group is what I would call deficient. It cannot be the full symmetric group. I mean, we know that typically the Galois group of a field extension, when you write down how you express the field extension, will be will be the full symmetric group. And when it's not, there's some special structure in the field. So this is an example of special structure coming from enumerative geometry that you're going to observe. Okay, and in fact, it has to be a subgroup. Well, this is what makes it such a special configuration. The special configuration turns out to be a subgroup of what we would call the Weil group of type E6. You can see the number 27. This is not Lie theory. I'm using Lie theory notation, but this doesn't come from Lie theory. It has to be a subgroup of E6, which is the automorphism group of this configuration. This is the configuration. Now, of course, for special cubics, the configuration could degenerate, or all the lines may be defined over the rationals, but for a typical cubic, it will be defined over a field extension of degree 27, and the full automorphism group of the configuration is E6. Okay, so there's a modern view on this. So here, P19, this is the space of cubics. So there are 20 monomials of degree 3 in these 4 variables. Don't make me do that in real time, it's easy count. And so therefore, a cubic, a polynomial defines a surface up to multiplication by a non-zero constant. So there's a 19-dimensional projective space of cubics, singular as well as smooth, but most are smooth. And okay, and then let me let G be the Grassmannian of lines in P3. This has dimension 4. It's a 4-dimensional homogeneous space. And I want to form an incidence correspondence. So this will be the set of pairs of a cubic together with a line such that F restricted to the line is identically 0. So this is the incidence correspondence of lines that lie on cubics. And it's not hard to see by, say, by fixing a line and looking at the fiber that this is smooth and has dimension 27. That's because if I restrict a cubic to a line, it's a homogeneous cubic on the line that has 4 coefficients, and they're essentially linear. The equations of this happen are essentially linear in the coefficients, and so this is really an affine bundle over the Grassmannian. But it's of course most interesting if you project it down to P19, and then the typical fiber is the 27 lines on the cubic. Okay. Now this is a branched cover. Okay, I see why this is over to the side. And so, well, it's a branch cover. So when the cubic is singular, which is a hypersurface here, of degree 32 is sort of classical fact, that outside of that hypersurface it's smooth and there's always 27 lines. So it's a branch cover, and then over the smooth locus, it's a covering space. And this E6 is known to be the monodromy group of that covering space. It's the covering group of the covering space. It's been a lifetime since I took elementary topology, or even taught it. And okay, so that's known. But also, but in fact, sort of algebraic geometry. If I look at the function, I'm going to work over the complex numbers. It doesn't really matter. If I look at the function field of this L, so this over the function field of P19. By the way, these are isomorphic as fields. They're both rational function fields that transcend degree 19. But there's an interesting covering. This has degree 27 because of the fiber. And if I take a look at the Galois group of the Galois closure, sorry about all this notation, which I'll always be taking the Galois closure over this base. That this is known to be E6 as well. And the fact that these are equal is not a surprise, because we know that monodromy in situations is the same thing as the Galois group I think the earliest reference to this I know is an observation of Hermite with curves in 1840. And it doesn't matter that I'm working with the complex numbers. Both the notion of monodromy and also this makes sense over everything else.
Could you just move a little the board?
Oh, this way?
Thanks. A little, yes.
Oh, like this?
Yeah.
Oh, I see the. Okay, so yeah, I'm going to avoid these boards. I thought I might use them, but it looks like it's a bad idea. Okay. So, I mean, in fact, a situation like this arises oftentimes. So for any, okay, so for any branch cover, so I mean here B is smooth. Might as well. It's irreducible, and dimension x equals dimension b, and pi is dominant. Sorry for all these technical terms. Then this has a Galois monodromy group. In the same way as I outlined for the problem of 27 lines. Yes, please.
I'm sorry, but there you said you get all E7.
All E6
All E6, yeah. And here we said the action.
is a subgroup.
It's a subgroup, yeah. So.
Yeah. So yes. So let me say. So Jordan made this observation, and we now know that in fact it's equal.
Okay, so here it's equal as well.
This is 1870, or at least my reading of it. This is at least by 1979.
Okay. Postulary everything is all
yes.
right? Okay.
I mean, there's something going on here that requires some work. In fact, this is an obstruction that I haven't been wanting to talk about later. Is that you can find geometric restrictions on a monodromy group, but showing that it's as large as possible requires a little more work than I know how to do in some cases. But that's why it's called research, or maybe talking to colleagues who know more than me. So now this situation of a branch cover is very common in the area of mathematics that I work in. In algebraic geometry, this happens in enumerative geometry. Any decent enumerative geometric problem can be expressed in this way, like the 27 lines. Also maybe more flexible ones than the 27 lines. But also, and what's also interesting to me, and why I put applications in my title, is that oftentimes in the real world, or come from engineering, are problems where you have a parameterized system of polynomials, and their solutions give you a branch cover. And those all also have a Galois monodromy group. And because these come from actual problems in the real world, they more often than you might think, they have some special structure for which this is an interesting invariant. And I'll say a couple words about that later. Now, I'll say, to give me some, I'm going to make some terminology, define some terminology to make it easier to talk about these as we've been studying these objects. So a geometric problem, or branch cover, or maybe just Galois group, I'll call deficient if it is not full symmetric. And yes, okay. So because I just want to work on this. So when I first learned about this possibility of Galois groups in enumerative geometry in graduate school, when I read a paper of Harris, written a decade before in 1979. So he observed. I mean, he has a paper called Galois groups in enumerative geometry. geometry in Duke that year. And in this, I think this paper had a lot of effect on people, although it didn't result in a lot of mathematics for reasons I'll mention in just a bit. But he observed that in all, well, okay, so when I say all cases, I mean all cases he looked at. The Galois group was as large as possible. So by this I mean what we just observed about this problem with the 27 lines is that in classical, he did much more than that, but in a number of classical examples studied by Jardin and others, there is a restriction on the Galois group given to you by some symmetry of the solutions of the problem. And he observed that restriction, it implies the Galois group is a subgroup of a particular permutation group, and in all cases that's actually the general Galois group. That's the Galois group either of the family or of a typical point in the base, of which the reducibility theorem. And so this is somehow a principle that he observed. He didn't say this explicitly, but Fulton told me that this is Harris's observation or Harris's hypothesis or something. I think it's implicit in his paper. And the point is, if the group is deficient, if and only if there's some structure which completely explains that deficiency, some geometric structure. Now, as I said before, in subjects as diverse as numerical geometry or Schubert calculus in particular, and also in applications, particularly something called algebraic statistics, there were examples of geometric problems that have a deficient Galois group, and this deficient Galois group was observed that it was small, either typically experimentally, before we understood what the structure was that caused it. Yes.
So the deficiency is explained by the fact that 27 lines have certain intersections.
Yes. So that's a priori there could be something more that keeps the Galois group smaller, but no, this geometric structure we've observed explains everything about the Galois group, at least its size, and perhaps that's not surprising that should happen, but it requires some understanding. This is more of a principle which has been observed. So let me just give you an example of some structure that's maybe a little more pedestrian than 27 lines. I mean, 27 lines is really exceptional. But the following, in fact, the first couple examples of problems that we observed where the Galois group was deficient in both these subjects, and later the explanation came about, are related to what I'm writing down now. So suppose, this is very pedestrian. Suppose an involution, say, as dumb as this one, xy goes to yx, or some other transposition, or some of the transposing matrices acts on solutions. Okay, then, so this should act freely on solutions because this should be somehow something irreducible. So then the number of solutions is even, and the Galois group is automatically a subgroup of this group. I don't know how you prefer to write Reith products. I'd probably do it wrong for half the people, of this Reith product. So this is the vector space over the field of two elements to the nth power. You can think of just a sequence of plus or minuses, and this is the symmetric group that permutes the coordinates. And in most cases, it is equal to. So this is also known as a Lie group of type Bn, but it's not. The Weil group of type Bn, but it's not from Lie theory. This is just Cox's group theory. And in many cases, so in most cases, so in a number of cases, it actually is this group. But also, there's sometimes a more subtle thing which occurs, and this is interesting to me. A couple times it's been observed it's a Dn, which is the alternating subgroup of Bn. So we know of many cases where this is what we observe. Now, if you know there's an involution, you know this fact, but in fact, a couple of occasions, this was observed first, and then we discovered an involution. Or rather, realized there's an involution. I don't know, discovered is probably too strong of a word.
So
Yes?
the number of solutions should be 5, right?
Oh yeah, yes, yeah. So in all these cases, we have a geometric problem or some design or configuration problem where there are finitely many solutions given generic parameters. So I mean, otherwise it's a different question. We're not looking at a finite cover. Okay, so let me talk a little bit about let me talk a little bit about the Schubert calculus, which is where I'm going to which is where we've been investigating this, and also why we're doing it there. So the classical Schubert calculus. So I'm using a modern reading of this word. So Schubert, in 1879, wrote a book about enumerative geometry. That's where we have the term from. And he studied many, many geometric problems there. The following decade, he focused on the geometry and combinatorics and cohomology ring, if you may, or intersection ring of the Grassmannian. And over time, particularly in the last 30 years, when people talk about Schubert calculus, they refer to geometric problems coming from intersections of Schubert varieties, which are special, I'll say what they are in a moment, on a Grassmannian or flag manifold. And so the Schubert calculus, whereas when my advisor Fulton was a student, referred to all enumerative geometry, now it typically refers to that relating to the Grassmannian and flag manifold. So that's so just to forestall people, just to make sure people when I meet, I know about this. So this is this involves, I guess, these are problems. This any problem of counting, or any problem of counting, because these are enumerative problems, counting the linear subspaces meeting fixed but general linear spaces. So there are many types of enumerative problems. For instance, lines that are incident on a cubic surface, and Schubert calculus involves linear subspaces of a vector space or projective space that have a position with respect to other linear spaces that's specified in some way. Now, let me just give a classical example, which, as I learned, keeps being rediscovered. Valentina Jacob told me yesterday that she has some physicists that discovered this following problem, because they needed to solve they wanted to understand a computational question in a detector at DESI, the high energy facility
Discovered
in
recently?
Germany. What?
Rediscovered recently?
Yeah.
Okay.
Yeah, you should go ask her. She should be around somewhere. I saw her yesterday. So, I guess 15 years ago I was working with people in computational geometry who were interested in lines of sight, in degenerate lines of sight, and the Schubert calculus. This particular problem also arises there, and it was useful in that area. So, here's the first example. It's known in the mid-19th century. So what are the lines in free space? So it's really the free space we live in, but to make it a nice problem, we want to compactify it. That meet 4 given lines. So this is the first non-trivial problem in general position, of course. Yeah. So there's an implicit assumption here always that when you pose a problem or a system of equations, the parameters are taken to be general. If or rather, there's some parameter space for which you're taking a typical element in that parameter space. In this case, the parameter space are 4 tuples of lines, and so I want them to be general. And upon studying the problem, if you're lucky, you can determine what general means. Oftentimes it's rather hard, because as we know, the discriminant locus in any geometric problem or system of equations is probably the most difficult thing to understand. It really contains more information than we can extract. Okay, so the way to approach this problem is well, let's use some classical geometry. Is that given 3 lines, there exists actually unique a hyperboloid containing them. I mean, it's a nice exercise that there exists a unique one. That there is one is not hard. A hyperboloid is given by a quadratic polynomial, and restricting a quadratic polynomial to a line gives me a homogeneous quadratic polynomial which has 3 coefficients. So there are 9 conditions on a hyperboloid, homogeneous conditions to lie on 3 lines. And a hyperboloid is given by a symmetric 4x4 matrix, of which so you're looking at 9 linear conditions on a symmetric 4x4 matrix. There'll be a one-dimensional space of solutions at least. That one-dimensional space of solutions gives you your hyperboloid. But you can also do it just by hand. So let me just try to draw this. I'm sorry, like the rest of you, I went to university as a mathematician and not an artist. Maybe most of the rest of you, but on this hyperboloid, there will be 3 lines, which you can see. Given 3 lines is a hyperboloid, so it's easier to draw the hyperboloid first, of course. And also on this hyperboloid, there are 2 families of lines. These lines are going around in a particular direction, but I tried to draw this symmetrically. But there's a family of lines that goes in the other direction, and in fact. Every line in the second family meets every line in the first family, sometimes at infinity. And so the set of lines, the lines, so L1, L2, L3, so the lines meeting L1, L2, and L3 form a ruling of, H, or hyperboloid, a ruling of H, and the other ruling, they form a ruling of H because L1, L2, 3 lie in one ruling. And so now it becomes easy to see how this problem is solved. If you take a 4th line, it's going to, I don't know what's going to happen. This 4th line will meet the hyperboloid. That's going the wrong direction. So I have to draw a real picture. So the 4th line will come in to meet the hyperboloid it'll meet the hyperboloid in 2 points. Because this is given by a quadratic polynomial restricted to a line. And in each of these points, there'll be one line in the second ruling that goes to that point. And so the answer to the original problem is 2 from this construction. Not all problems in Schubert calculus can be understood this so explicitly. So now, either using basic fact that the Galois group is a transitive group on the solutions, and there's only one transitive group on 2 elements, or perhaps just taking this line and rotating it around until it comes back in place, but these 2 points of interchange, you can see that there's a monodromy permutation. Fixing the 3 lines and rotating the 4th one, which interchanges the 2 lines, because as L4 rotates, the 2 lines have to move with it. They're dragged along and they interchange position. So the Galois group is S2 here. So this is full symmetric, or not deficient. Okay, so and Schubert calculus involves much more complicated, but completely understood problems. This is one where I can actually write down. Okay. Okay, so now this Schubert calculus has long been a laboratory for studying phenomena in enumerative geometry. I mean, originally Schubert determined what we now call the cohomology ring of the Grassmannian, and that later led to a lot of interesting. I mean, understanding that calculation took a lot of work, and of course was generalized vastly. And there are many other examples where this class of problems or this class of varieties has been studied to give us insight that we later understand is quite general. And now, one reason for this is it's sufficiently complicated yet sufficiently simple we can understand it completely. So, for example, because of work that has been done before, we know every Schubert problem, meaning we can describe them completely. It's a discrete problem, and we understand what their number of solutions is in some sense. And
Maybe we can state them.
we can state them, yes, in that sense. By understand, I mean, in fact, we don't understand them, but we can list them. We know the number of solutions, and that's already a start. It's not like Gromov-Witten theory, where we're still understanding, where there are things that people are still understanding, or maybe 30 years ago people didn't know how to do curve counting. Now we know how to do that. This has been settled for, well, depending on how you think about it, since the 1930s, but actually maybe since 1947, when people first made the link between representation theory of the special linear group and the Schubert calculus and Grassmannian, or it's been certainly understood in my lifetime. Now, also, another reason that this is worth studying is there are, I think, thousands to maybe hundreds of millions of computable Schubert problems. What I mean is there are a large number of Schubert problems that we sort of understand what they are in terms of the geometric question, but we can formulate them on a computer with coordinates and solve them in some sense, either symbolically or numerically, and then study the solutions using a computer. An approach one can use to getting information about some aspects, or facets of the Schubert calculus, can be computational using large computers, what people might now call big data. And so, for an example, because we didn't have any good ideas how to solve this, so my research team, we used maybe 8 to 10 terahertz years. So this is a dimensionless constant of computer time here, studying reality. There are some conjectures that were made by Borish and his brother, and then later generalized through, or discovered what the generalization would be through computer experimentation. Some of the conjectures were proven spectacularly by Sasha Pachenko and his collaborators and Gabrielov, and some other conjectures have recently been proven about lower bounds, and there's many other things we uncovered by studying reality on a computer.
This is complex space or real?
Oh, this is reality. Okay. Meaning you formulate the problem using real objects, and you ask about the real solutions. And it's really, it's an amazing topic. What people have conjectured, what's true, and what they've discovered, and particularly the method. That's often what happens. And because of this good understanding of the geometry and combinatorics of Schubert problems and the computability, I've been with collaborators for some time been studying Galois groups of Schubert problems. So with many others, and some will be mentioned, we are studying. Sorry about my handwriting. I have to always apologize about my handwriting. It's been really poor since I started to write, and I sometimes, I mean, I'm actually pretty good today. Sometimes I have order problems writing. But we are studying Galois groups. I should say that and I'm going to sketch this the remaining time that I have. So in 1979, when Joe Harris wrote his paper on Galois groups for enumerative geometry, he came up with a very simple-minded method which fit well with things we knew geometrically for showing a Galois group was the full symmetric group. I mean, simply put, if you can find a position of the conditions so that there's one double solution, then you know there's a simple transposition in the Galois group. And because it's a transitive permutation group with a simple transposition, it's the full symmetric group. He used this to show that many problems that generalize these classical problems that Jordan looked at, many of their generalizations were in fact the full symmetric group. So for instance, the 27 lines in the cubic surface, this is a family of problems which are interesting for reality. Now, you can look at the number of lines on a quintic threefold, degree 5 and P4, and the number is either 2715 or 2815, I don't remember. Maybe you remember? The number of lines on a quintic threefold? Anyways, it's 2,715 roughly, and Joe Harris showed, using a construction, that in fact that was the full symmetric group. So only the case of cubic surface is an exceptional. But the one reason that there's not been much work on Galois groups since then, and we've talked to people about this, is that there are no methods, or there are not very many good methods for computing them or studying them. And while I was aware of this in graduate school, this is, I mean, once it became clear that I was interested in enumerative geometry or reality, Bill Fulton, who was my advisor, suggested that I think about Galois groups. Well, I thought about them and had no ideas. So you only work on something if you have an idea. But what's happened in the last, I guess, 18 years is there have been some methods which have emerged, and also we came to realize that there were methods already out there that we didn't try yet. So let me sketch something about some of the methods and some of the results that we've had, particularly for Galois groups of Schubert problems as I've defined them. So what got this started, what got me thinking about this again, was Ravi Vakil, and then Derksen, and then I looked at and then my group, we looked at the data we computed, studying reality, and I'll also say my group, but this is after what they did, discovered they found infinite families of deficient Schubert problems. Now, when this happened, there was a little bit of a surprise.
Not just due to an evolution,
More complicated. In fact, both of these examples are more complicated than just an evolution. And what was also so in hindsight, it's clear that this should happen, but at the time it was surprising. And the reason is that from the work of Harris, it seemed that once you got past these exceptional examples, everything would be the full symmetric group, because that's what he showed. I remember being surprised, and I remember talking again with Fulton that he was also a little surprised. But I mean, you know, facts are facts, and you quickly take stock of what's known in the world. And okay, so I should say that they are in every Grassmannian. So my group, we found them in flag manifolds, and I'm going to leave flag manifolds aside because we haven't studied it yet. In every Grassmannian, so the Grassmannians are parameterized by, okay, so this is k-dimensional subspaces of, I'll say of Cn. It doesn't matter. It's actually the same whatever algebraic field you work over in terms of the Galois group. Okay, where 4 is less or equal to the minimum of k and n minus k. The Grassmannian of k-planes in n space is isomorphic to that of n minus k-planes in n space, and so this happens. So once the Grassmannian is sufficiently large, we can always find efficient problems in it. And of course, since then, there have been many other examples found, and we've been studying this. There are other infinite families, particular examples that we've discovered and thought about, and every Galois group has, let's see, every Galois group we've determined, okay, so I should point every Galois group is one of, so this means that which we have determined, and I'll tell you what we found, and it's not very many groups can occur, but that's already kind of interesting. It hints at something in the structure. So, okay, so first of all, it's either the symmetric group of m letters acting on some ordered partitions of the numbers 1 up to m. So, for example, S4 acting on, say, two partitions, which what I mean is 1, 2, 3, 4. So the straight line is the partition. 1, 3, 2, 4, 2, 4, 1, 3, 1, 4, 2, 3, 2, 3, 1, 4. So there are 6 ordered partitions of 4 and 2 parts, and S4 acts on these. In fact, this action. It's okay. So if this is actually D3. I mean, the way we understand this is here. This is an action of D3. You see that the bio group of the Cauchy group of D3 is the same as A3, which is S4. And this, in fact, was the original example that was found, both in Schubert calculus and in algebraic statistics, where there are 6 solutions and it ends up acting on pairs. Okay, or so it's either this group or, and I'm going to go to the board which writes well. What's the phrasing I want to use? Okay. Yes. So it's either it's either that, or in fact this is a recursive description, or an iterated wreath product of groups of type 1, meaning. If you don't start, essentially iterated wreath products of groups of that form. So for example, this Bn is Z mod 2's wreath Sn. Is an example of an iterated wreath product that we already looked at. Yes, so the constructions we know are of this form. And nothing else. So no Matthew groups, no cyclic groups other than Z mod 2. So that's what's been discovered. Let me tell you what we know and what we're thinking about. So what's striking is there's a dichotomy. So this refers to the classification of permutation groups. So every group. Again, every group we've identified is either full symmetric or imprivative. So in the classification of permutation groups, you can look at you can ask how do they move elements around, and the symmetric group is fully transitive. You can take any list of n elements, any other list of n elements. That's what it means to be the symmetric group. Imprivative says that there's a partition of your elements which this group preserves, so this is far from being full symmetric. In fact, these are not even too transitive. They really don't have very many transitivity problems. There's a large gap. It doesn't. This dichotomy has been observed.
Is it an experimental fact so far?
It's an experimental fact, but in some work with Jacob White, we begin to see how this could come about. I may not. Maybe I'll say that in a moment. Okay, so let me tell you how we found out this information and what are some things we know that are maybe that inform this. So in the first work of Bakil that I mentioned on this board before, he gave a combinatorial. Maybe it's also geometric because it relies on some geometry. Method, and the phrasing is important, that can show a Schubert problem. This, I mean, it's a more general idea that it's Schubert problems, but because of his geometric Galois-Richardson rule, it applies to Schubert problems most readily. On a Grassmannian, contains, has Galois group containing the alternating group. So it can imply that a Galois group is either the alternating group or the full symmetric group. It can't distinguish between them. And so I'll call this at least alternating. I mean, one uses the tools that one has at hand, and so we can show a number of Schubert problems are at least alternating. It's believed they're full symmetric, but without more knowledge, I can't say more. Maybe at least now. Okay, so here are some examples. All Schubert problems I'm going to talk about the Grassmannian. On the Grassmannian of two planes in n space, which is isomorphic to the Grassmannian of n minus 2 planes in n space, are at least alternating. So we're using Bakil's criterion and some either some very complicated estimates of combinatorial numbers, or using some more geometry and then some less complicated estimates. There's two different proofs. We can show this. I mean, this was shown with a former graduate student who works at CMOD in Mexico. This is Martin Del Campo. That was his thesis. Another example of something that's known is all problems. I'm going to drop Schubert on the Grassmannian of 3 planes in n space, or its dual Grassmannian, and what are called special Schubert problems. These are Schubert problems where the condition is a simple incidence condition. So these are ones where dimension, the k-plane meets a fixed n plus 1 minus k minus a plane. non-trivially. So this is called a special condition, that there's only one condition, and it's a simple incidence condition. So if you only have those, then these are at least, these are two transitive. So are two transitive. And that's with White, who works at University of Texas in the Rio Grande Valley. And this involves showing that a second fiber product, just a simple fiber product of my total space I've written down before, is irreducible. Because these questions about transitivity can be expressed geometrically.
But this is a weaker thing.
Yes, it's weaker, but however, because of this dichotomy, so two transitive already moves you off of class 2. And one of Vauquel's methods, the reason we're looking at two transitive, is if you can show that certain intermediate problems are two transitive, and that they don't have 6 solutions in some degeneration, or some other work, which is a finite problem, then you can imply that it's at least alternating. So two transitive is already kind of powerful, and one reason we expect a dichotomy we can see already in this geometric combinatorial method of Vauquel. I mean, his method is essentially, so in numerical geometry, one of our more powerful tools is to take geometric conditions and to generate them so the problem splits up into two sub-problems. And that's called the method of special position. And conservation of number tells you you count each of these and then you count the original problem. But there's a Galois theory correspondence here. If I know that the Galois group of this problem at least contains the alternating group, and the Galois group of this problem at least contains the alternating group, and if the numbers are different, then it's a group theory result. Then the Galois group of the original problem is at least alternating. But even better, if the total problem is two transitive, and these are not both 6, because the Matthew group is a counterexample to that, then it's at least alternating. So there's a group theoretic result. Okay. And okay, so there's also, I mean, I might as well list them since I have a couple more minutes, and then talk briefly about classification. So also something called simple Schubert. This is a technical term. Are two transitive. And this means that all conditions except 2 are what I call codimension 1. This is also with White. For me, this is what got me started here, or at least when I started thinking about Galois groups. One of the first things, once I saw Vauquel's or Derrickson's work about Galois groups, I realized that methods that my friends and I knew about can be Galois groups because they are monodromy groups. And there's an area of applied algebraic geometry called numerical algebraic geometry, which uses tools for numerical analysis to study algebraic varieties on a computer. And it's set up, and the most natural computation in this field is monodromy. And so computing monodromy of a covering space is quite easy in this field. And so with Untitled, we decided to investigate this, investigate some Schubert problems, actually these simple Schubert problems on a computer. The reason we chose simple Schubert problems is there's an algorithm for solving them. They're very numerically, which works very effectively. And every simple Schubert problem we studied, we found had full symmetric Galois group. And the largest such problem was one that had 17,589 solutions. So we set this up on a computer and solved it. It took about 20 hours to solve it. And then we computed monodromy permutations, again on a computer. It took about 3 days. And found, after 7 of them, we found we had enough to generate the full symmetric group. So trusting the calculation, which you may or may not want to trust, but it is what it is. We observed they were full symmetric, and we believe that this would be true for this whole class of problems. Simply because there's no reason there's any symmetry, there's no reason there's any special structure there. Okay, and I want to say that in all these cases where it's at least alternating, we expect it's full symmetric. And we've tested every simple Schubert problem having less than 1,000 solutions and showing that it's full symmetric using symbolic methods, not numerical methods. Okay, so now more recently, so we studied some of these people as well as Robert Williams, we studied. Okay, so I mentioned earlier that these deficient problems are only found on Grassmannians of 4 planes in 8 space or larger Grassmannians. And so we studied all, you see, 3,501 or 36,767 problems on G48, which is the first Grassmannian where anything interesting happens, and here G49. So we looked at all of these, and we first of all used Vauquel's common color criterion. He has an implementation of this in Maple that takes about a week to study G49, but we also wrote our own software in a more robust, or in a faster computer language, which takes about 2 minutes or 2 hours to compute G49. So we studied all of these, and his method gives you a way of determining, telling you that it contains the alternating group, but there are problems that it just says we can't tell. And so of those you couldn't tell, so of those that failed Vauquel's criteria, we either used other methods like coming from these results over there, or we just computed I guess, well, you can compute cycle classes. How do I want to say it? We can compute we computed cycle types of elements in the Galois group. So this is the symbolic computation you can do. You solve a problem, set up in a computer, reduce mod p, and then solve it, and then factor the result, and the factors, if the polynomial, the univariate polynomial, you get a square free, the factors give you the cycle type. So we can compute cycle types of elements in the Galois group, and from examining those, you can determine if it's full symmetric, or you can get a good idea, because in fact a very good idea, because the Chebyshев density theorem applies here, of what the Galois group is, and there were 14 or 148 that we found were deficient computationally. Now, of all of these, we then went we then went and studied their geometry and was able to show that they had some geometric structure which caused the Galois group to be a subgroup of a particular group, which we'd already determined it had to contain that group, and so we determined the Galois group on these. We also computed, using this method, the cycle types, we computed every problem on these, which had, say, fewer than 500, maybe it's 600 solutions now, and showed that it was full symmetric. So the point is, however, not only do we do this, but from looking at these problems, there are different geometric reasons for each one of these problems to be deficient, but we found that there's actually only 3 reasons so far. One that applies to a problem here, which is the original problem of Vauquel. 2 other ones that apply. So in here, there are 3 classes of reasons why it's deficient. 3 different reasons. And here, there's either 11 or 3, depending upon, or maybe 4, depending on how you classify it. But this suggests to us that it could be possible, if we do a little more, to actually classify these deficient problems. But that's where this stands. We sort of don't know what's happening. We certainly understand there's more structure in Schubert calculus than before, and well, it is what it is. And I think I'm out of time now. So thank you.